So it is my pleasure to welcome the 2018 Nobel Laureate in Physics, Professor Donna Strickland, to Stellenbosch University. I really would like to thank you for accepting our invitation to join us at the university and to be able to grace the presence of the Stellenbosch community. So Prof. Strickland is in South Africa due to the 26th Congress of the International Commission for Optics, which we are hosting on the African continent and in South Africa for the very first time. The International Commission for Optics has been around since 1947, and they are Category 1 member of the International Science Council. They are associated with 53 territory committees. And what I'd like to announce is South Africa, as of today, is now joining the International Commission for Optics. So it has been endorsed by ASAF this afternoon and approved by the ICO. So now South Africa is the newest territory to the International Commission for Optics. So we look forward to Yes, we look forward to many more endeavors with the ICO. So without further ado, I would like to welcome Prof. Donna Strickland to the podium. Prof. Donna Strickland is from the Department of Physics and Astronomy at the University of Physics in Waterloo, Canada. And as we all know, she's the recipient of the 2018 Nobel Prize in Physics for the development of chirped pulsed amplification with Professor Gérard Mourou. And I don't want to steal too much of her time, so I will let her focus on the research that earned her Nobel Prize. Over to you, Prof. Strickland.
Show? Okay, excellent. Well, thank you for this invitation. I also want to appreciate that so many people are coming to hear this talk for a second time in 2 days. That's really impressive. I also have a shout out from a colleague, Sikazi Matanga, because he's told me that it was this Theoretical and Computational Institute, which is really weird because I'm an experimentalist, but I appreciate that a Theoretical and Computational Science Institute would help host me. And to the Stellenbosch University community, thank you very much for having me. So I am going to give a talk about what I did to win the Nobel Prize. And to understand, I guess, the importance of it, and understand why I did what I did, I do like to go through the whole sort of history, because it's not just one person doing science. It is a whole trail of people and science being done that makes this all come together. So we're going to go back 150 years at least, well, more than 150 years, when scientists were still grappling with, what is light? Is light a wave, or is light a particle? And there was reason to think both, right? But finally, it was a theorist who laid down the theory for everybody, and it was such a strong theory, everybody had to agree that light must be a wave. But they still wanted to prove it, and so they started to think what experiments could prove it. And so just like if you're walking and you're pretty much here on the ocean, I don't know about Stellenbosch, but Cape Town was on the ocean, that, we all know that if we walk along a beach, especially if you think about a stony beach, when the waves are just small ripples, stones don't move on the beach. But when the waves get very high and they come ashore, they can throw the stones quite a ways up the beach. And so we sort of know in our heart and soul that the power in a wave comes from the height of the wave, not the distance between the crests. And this was also true for the optical wave. It should come from the height, not from the distance between the crests. So I'm only going to talk about the light that we see with our eyes. And so we see light from red to violet. And so what we call the distance between the crests, we call the wavelength. And red has the longest wavelength that we see. Green is the one we see in the middle. So we see green the best, which is why I use a green pointer if it's on. Yep. And then violet on the other side is not quite a factor of 2 less of a wavelength. All right. And so for those of you who are musical, you'll think in octaves, which is a factor of 2 in the audio frequency. We don't quite see a whole octave of the whole electromagnetic spectrum. But so they used these different colors of light, and they did an experiment analogous to water waves on a stony beach. They're going to shine the light on this material, and they're going to watch the electrons come off the material. And then they're going to turn up the power, and if light's a wave, the electrons should come off faster. So they tried it with different colors, and when they used red light, no electrons came off. It didn't matter how powerful they made that red light, electrons would not come off. But when they used green light, the electrons came off, but at very low energy or slow speed. And when they turned up the power, more electrons came off, but at that same slow speed. And finally, when they used violet light, that's when the electrons came off at high speed. And when they turned up the power, more electrons came off. But the speed seemed to go with the inverse of the distance between the crests. This is what we would call the frequency. And so once again, scientists were left scratching their head as to what that could possibly mean, because it sort of flew in the face of light being a wave. So now, at about the beginning of the 20th century, Max Planck showed us that if you turn down the power of a light beam, then the energy or the power could not change continuously. There had to be a minimum energy unit. And this minimum energy unit is what we now call the photon. And he also showed that the energy of a single photon would be dependent on the frequency, or the inverse of that distance between the crests of the wave. So again, if thinking about how we understand energy, gravitational energy is the one that we sort of experience in our everyday life. We know if we want to pick up something really heavy, it takes a whole lot more energy to pick it all the way up, okay, than just to barely get it off the ground. We know that, well, I don't know, do you guys get snow here? I'm from Canada. So the example I use is if we want to sled fast down a hill, we know we have to start at a higher hill. In any case, we know that energy goes with height. And so I'm going to talk about the energy in terms of height. And so you can think of red photons as being child-sized photons, and they can only lift an electron that high up. And a green light will be an adult-sized photon. And finally, the violet light is going to be like a basketball playing photon. I don't know how big basketball is here. The one time I was in Spain, I said that, and they came afterwards and let me know there were no more Olympic basketball prizes in Spain than Canada. And I went, okay, didn't know. Anyway, hopefully you've all seen the game. It began with a Canadian, though, just saying. All right, now, why do I even mention that? I'm going to explain this effect of the electrons coming off using an analogy with basketball. And we're going to imagine that our photons are playing basketball with a child-sized net. So it's only going to be this high. So this is what Albert Einstein explained to us, but I'm going to explain it in a slightly different way. So imagine these child-sized photons trying to dunk their basketball through the net. Even on their tippy toes, they cannot do it. If you imagine trying to turn up the power in this photon picture, it just means that the density of photons has gotten denser. So you'd have a lot more photons all around this basketball net, but none of them can dunk the ball or the electron. So none go through. Now you can have adult size playing photons. And this is why I only play basketball with a child-sized net. Because as an adult, you can dunk the ball, but you're only just barely above it. And so when the electron goes through, it goes through at a slow speed. Again, if you turn up the power of the green light, there'll be more adult-sized photons all around the net, dropping their balls in slow speed. And finally, when you get the basketball playing people with a child-sized net, just by standing there and dropping the ball, it's going fast through the net. So this is how you can understand the photoelectric effect. So there's a few reasons I choose this one as a linear optical effect. The main one is that for all the things Albert Einstein could win a Nobel Prize for, the thing he won in particular for is explaining this photoelectric effect. It's also what I ended up doing for my PhD, but in the high intensity laser regime. So that's the other reason I'm going to talk about it. But when we explain it to our undergrads, we're always talking about it being this beginning sort of understanding quantum mechanics. But for this talk, it's really an example of a linear interaction of light with matter. And what I mean by a linear interaction with light and matter is that it's always one photon interacting with one atom at a time. And if the photon energy is bigger than what the atom is holding onto its electron, the electron gets to leave with the difference in energy. Now, if you double the power, then you will find those many more photons would find that many more, double the electrons, and that's why more electrons go off. And if you triple, it triples. And so the current would triple if you triple the power. So it's linear. Okay, so it's a linear interaction. It's one photon interacting with one atom at a time. And so I'm sure at the beginning of the 20th century, and Albert Einstein explains this to us and everything, we probably think we really get how light and matter interact, and we're done. And then along comes this woman, Maria Goeppert-Mayer. Now, she's famous for being the second woman to win a Nobel Prize in physics, but that's for work she did at Argonne National Labs in the 1950s about nuclear shell model, which I know nothing about, so I won't discuss her Nobel Prize. But when she was still a graduate student in Germany working with Max Born, she's the one who asked the question, why can't an atom absorb the energy of two photons at the same time? And she went through the theory and she showed us that it would work. Now, she showed it for two photon absorption, but we're going to stick with the ionizing or the electron coming off the atom. If we could have the absorption of two red photons, then together, standing on the shoulders of the other, they would have the energy of not only violet, because I told you that's not even twice, it would actually be in the ultraviolet, but I can't show you ultraviolet, so we're just going to stick with violet. And so we would have this absorption of two photons, the energy, and it would look like from the electron coming off that maybe it was just one ultraviolet photon. And she worked on this for her thesis in 1930, and she published the paper in 1931. But nobody saw this happen until 1961. And the question is, why did it take 30 years for someone to finally see what she showed us should happen? And so it was first done in Peter Franken's group, but it was not quite, again, it wasn't two photon absorption and it wasn't two photon ionization. What Peter Franken's group did was something called second harmonic generation. In this case, the atoms simultaneously absorb the energy of two red photons, but they don't hang on to the energy like absorption, and it's not enough energy to kick an electron off. Instead, the atom lets go one photon with twice the energy. So again, it would have let go an ultraviolet photon. Okay, so they finally saw this in 1 part in a million to 1 part in 10 million. And so then it begs the question, why did it take 30 years for us to see what Maria Goeppert-Mayer told us we should be able to see? And the reason is that we needed the laser to make it happen. And so Basov and Prokhorov won the Nobel Prize along and they were working together in what we'd call Russia now. Towns was in the United States, working independently of them. These are the three gentlemen that are considered to be the inventors of the maser. M stands for microwave, where L stands for light. A microwave is a lower energy photon, and technologically it's easier to show it. So they showed the maser first. Shallow then won a few years later for laser spectroscopy, but he's one of the people that figured out how to change the technology so it would work for light. But although those are the four that won the Nobel Prize, it's really this man, and I don't know why he didn't get to win the Nobel Prize. Ted Maiman is the first one to demonstrate a working laser. He was working at Hughes Aircraft, and he demonstrated it on May 16th, 1960. So what's so special about a laser that would make this nonlinear effect happen? Well, first, there's a lot of bright lights on me and we're all lit up here. And that's because normal light coming from light bulbs, we're white light because that means if we see white, it's because every single color we see is being shown. We're all being lit up right across the room because a light bulb sends the photons in all directions. But most importantly, the photons don't care how each other are operating. Every photon chooses for itself when to go, and it doesn't care what the others are doing. But I'm using a laser pointer to show these screens here. Oops, I only have one. These people don't get anything. Can you see the screen? Okay, so they're all, you can see that I have this bright green dot on my screen, and that's because all of the light coming out of here goes in a straight line. All of the photons go in one direction. They're all the same color, but most importantly, they all know what each other are doing. When one's peaking, they're all peaking, and one's troughing, they're all troughing. And so when you add these waves up, classically, then it can be a giant wave. But I like to think about it in the photon picture. So now I like to say that if, in regular light, if you have all the different colors, they're all dancing to their own beat. And they're all dancing, I can't actually make my hands go 2 different times, but if I could, I would show that. But they don't actually care how anybody else is dancing. So unlike when South Africa actually led us at Linda with this great big dance party, we all crowded onto the dance floor, but these photons cannot. And so we can try to increase this density of photons by using a lens and bringing the beam down. But you can only focus to a single wavelength of light, which is about 1/2 of a micron. And just so you know, your hair is about 50 microns. So we can focus 100 times thinner than your thickness of your hair, which seems very small. But when you think about it, a single atom is still 10,000 times smaller than that. So now, if you ask, what's the likelihood, probability of having more than one photon in the interaction volume of an atom with regular light? It's just too small to be seen. But when the laser came along, and I will say that Nicholas Bloomberg won his Nobel Prize with Art Shallow for laser spectroscopy, but he's considered to be the father of nonlinear optics, so I left him for this picture here. So now, all of the lasers, all the photons are dancing to the same beat, and they're all dancing together to the same beat. And that's the reason that they can crowd onto the dance floor. So that when we did focus laser light down onto an atom, there was that chance in 1 million to 10 million that there would be 2 photons at the same time in that interaction volume. And so we could see the absorption, simultaneous absorption of those 2 photons. So what has any of this got to do with me? When I joined Gérard Mourou's group, everybody else, I was like the 7th student. The other students were all working on making the pulses shorter to measure something faster. I was the first one tasked with trying to use short pulses to make the power higher. So I'm going to explain that coming up, but that's why I'm the one who got to work on this. And the experiment that we were going to try to do is called high order harmonic generation. Not 2 photons, but a lot of photons. And it was a paper that I read from Stephen Harris of Stanford University, who had come up with the way to get this high order harmonic generation to happen. And so I looked at the paper and I figured out that I could maybe see the 9th harmonic, and really forget ultraviolet. I was going out into the vacuum ultraviolet with my 9th harmonic of infrared photons. There was 2 parts to my project. One part, I had to make the cold plasma of twice ionized nickel, which I'm not going to explain to you, and it doesn't matter because I never figured out how to do it. So that whole part of my thesis just didn't work. But the other part of my thesis was to figure out how to make the laser really intense, because I didn't want to just absorb 2 or 3 photons. I had to absorb 9 photons. So I had to have a really big density of photons. And that part of my project obviously worked, because that's why I'm here talking to you about it. So how does one do it? So even though I've been working in this field for over 40 years now, I'm still amazed at how fast light travels, okay? So I can make a 1-second light pulse I could do it on the ceiling too, but I'd make you all look up. Okay, so especially if the moon was there, if I knew where the moon was, I could aim for it because that's what we're going to do. But I can make a 1-second light pulse just by opening and shutting my finger here. And if I did that, and there was a window here and the moon was outside the window, the front of that laser pulse would be almost 3/4 of the way to the moon before I would shut my finger, shut it off with my finger, which I find amazing that you can get almost to the moon in 1 second if you could travel the speed of light. And I can just tell you how many hours it took me to get here from Spain, not even from Canada. And so it would be nice to travel the speed of light. All right, so that's how fast light travels, and that's a 1-second light pulse. So a 1-second light pulse, which doesn't seem very long, stretches 300,000 kilometers, okay? So you'll also see that I have a millijoule of energy listed. So why do I talk about a millijoule of energy? There's 2 reasons. One, the paper that won me the Nobel Prize was about a laser that only put out 1 millijoule of energy. And 2, that's enough now to cut glass, which I'll explain at the end of my talk. But again, this is also to make sure it's eye safe. It should not be more than a milliwatt. And power is energy per unit time. And so every second coming out of this 1 milliwatt laser beam, right, in 1 second, is 1 millijoule. So if I hold it on my hand as steady as I can almost feel that part of my skin warming up, all right? So a millijoule of energy just doesn't seem like very much. So what's the difference? Well, first, remember it's the density of photons. So 1 second at 1 millijoule spread over 300,000 kilometers. The first experiment done in nonlinear optics with lasers it did actually use 1 joule, so it did use 1,000 times more energy. And it was down to a millisecond. Now, a millisecond really seems fast to us, but a millisecond is still 300 kilometers long. It's still a long line of light. What we did with CPA was bring it all the way down to a picosecond. A picosecond is a millionth of a second, or all of the energy that comes out of here that would stretch out over 300,000 kilometers is now squeezed into 1/3 of a millimeter. And that's how we got the density of photons up. We squeezed them from 300,000 kilometers down to 1/3 of a millimeter. So I like to say that I built a laser hammer. So, you can try to push a nail into a piece of wood and push with all your might, it doesn't go in. But if you pick up a hammer, in it goes. And it's because sometimes the applications depend on energy, and sometimes it depends on the energy per unit time. So let's go back to Earth to explain how we did it. And so I'm going to take you to Rochester, New York, where I did my PhD. And I did the research at a Department of Energy funded facility, the Laboratory for Laser Energetics. This facility on the campus of the University of Rochester is for laser fusion. So it was a fellow Canadian that met me my very first week in Rochester, who took me over to introduce me to Gérard and also show me this beautiful lab of his. And it was for a dye laser. And a dye laser is this beautiful laser that lasers in the red and is pumped by the green. And this is the jet here that dyes, actual liquid dye is flowing through this tube into a jet. And it is like if you got that on your clothes would be dyed orange. So that's what's called a dye laser. And so it's a beautiful laser. And I just thought, this is how come I decided to work with Gérard. I just walked into the lab and thought, oh my goodness, how much fun would it be to work around this laser that looks like a Christmas tree all year long. And I just thought I have to work here. So that's why I chose to work with Gérard. Anyway, people think it's maybe some deep and wondering, physics. No. Okay. So this is an example of a short pulse laser. So Gérard already had them in his lab. And in fact, this one is 10 times shorter than what I'm talking about. He already had lasers that could do 100 femtoseconds. Okay, so that'd be a 30th of a millimeter. But this kind of laser cannot be made energetic. And so we had short pulse lasers to measure things fast, but it wasn't going to be powerful. Right across the lobby is the laser for laser fusion. And fusion is one of the applications that depend on energy in to get energy out. And so just a few years ago at the National Ignition Facility, we finally put 3 megajoules in and got more than 3 megajoules out. So that was a big success. This is the way the laser looked back in the 1980s when I was there. It's 24 beams and it was a kilojoule of energy. And so this is a big energy laser. And so on one side of the laboratory for laser energetics, we had very short pulses. And on the other side, we had this very energetic laser. And I do want to give you a scale of this picture. This sits on a football-sized field, doesn't matter what you call football. So, and this thing here is the size of a human adult, okay? So this is a big laser. And you need a big laser if you want a kilojoule, and obviously the megajoule laser, even bigger. So we had both short pulses and big energy, but we couldn't put them together, okay? And we couldn't put them together because if we did, we caused damage. We had the laser hammer hammering the amplifier. And so that didn't work for us. And so we were told not to do that anymore. And that's why we needed to develop chirped pulse amplification. So this is Gérard's and my picture from the Nobel ceremony. This is not one of the official ones that I've been showing you. This is one that a friend of ours, colleague of ours took of us. And I should change it into black and white because I used to say when I made this talk, it's in color because we're the present day and the rest were history. But of course, I'm history now too. And so is Gérard. Anyway, it'll stay color. So here it is. This is my laser hammer. This is what I want. I want a lot of energy in a very short pulse. I don't want my laser hammer hammering my amplifier. So this is the whole idea. So we're going to take a short pulse and we're going to make it a long pulse. And when we have a long pulse, now we have the density of photons down low. So now we can amplify it up and get it up so that the density is enough, but not enough to cause damage, not a hammer. And then when it's safely out of the amplifier, we compress it and make the hammer. Now, in my day, with the energies that we had, we could do it in air. But with the biggest ones now, they have to be in vacuum because even the air we breathe becomes a nonlinear medium for the most powerful lasers that we have today. So that's the whole thing. We could have called it stretched pulse amplification because that's probably a better name for it to tell people what we're doing. But because we use dispersion, which means the different colors travel different speeds, it ends up being that the colors change in time through the pulse. This is the same as the audio frequency in a bird's chirp. And that's why we call this an optical chirp. And I guess we just thought chirped pulse amplification sounded better. So that's why it is. So that's all it is. All right, so now let's go back and explain how it actually worked. This looks like it's the very same laser as I showed before, because it is. But I've changed the title. That's because we're going to not look at this part anymore. We're going to look at the part that makes a laser beam that we cannot see. Okay, so this is the neodymium YAG laser. And even though we need the green to pump the dye, it's actually coming out as infrared at 1 micron wavelength. This box here is doing the frequency doubling. The Peter Franken's group did in 1 part in 1,000,000 to 10 million. But now this laser is intense enough that we got 10% conversion into the green. So so the light comes here that's infrared, 10% turns to green. Our laser mirrors are really good for the color they're supposed to be really good for. So 99.99% of that green is turning the corner, but the infrared is coming right through. So 90% of that power was doing nothing. It was just sitting there. So that's what Gérard gave me to do this project with. It was just sitting there, I could use it. But you can also see it's very crowded and there's really no room for me. But I have a picture of me in the room. I didn't work very long in this room, but that's because here's my fiber. And here's where the beam dump was, but this is now a fiber mount. And we launched the light into the fiber. And the fiber had to do really 3 things. One, it had to make colors. And in my public talk, I don't explain that part. So we're just going to ignore that part. Number 2, it's going to be my pulse stretcher. Okay. And that part I'll explain. And 3, there's no room for me in the lab. And so we had to, once I got the light through the fiber, we actually strung it through the air ducts right across the whole length of the laser lab to an empty lab so I could build the rest of the system there. Luckily, I'm very claustrophobic and afraid of heights. So my colleague crawled through at midnight because we weren't actually allowed to do that. So I even got out of doing the thing we weren't actually allowed to do. It was very nice of her to do that for me. Anyway, so those are the three things it was supposed to do. I think that's, I told other stories the other day, but half the crowd's heard them. So I don't think I need to tell the other stories. All right. So, but I do need to tell you that we need to make colors. For this kind of laser that's on all the time, I told you it's just a single color. But if you have just a single color, it has to go on forever. If you want a short pulse, you need to have all the colors. And you need more and more colors if you want to make a shorter and shorter pulse. All right. But we can't have like the white light that's coming out of our lamps. Because if you go to an orchestra and you listen to everybody warming up their instrument before they actually all start playing, it sounds like noise because each person is playing their own note and they don't care how anybody else is playing their own note. And that's why it's just the same as the light coming out of the light bulb. It's just noise. But when the conductor of the orchestra brings down his baton and they all play their notes together, then they make beautiful music. And so we have something like that conductor in our laser. It's called a mode locker. And you also need a special kind of laser that allows a lot of colors to laze. But it says to all of the colors that can laze, go here, go now. Now the black line is the addition of all of these colors. But as you go away from here, because the different colors have different distances between the crests, you can see that as you go, they come apart. And by the time you get here, there's as many peaking as troughing. So when you add them all up, it sort of adds to zero. And the more colors you bring in, the faster this happens. Okay, it's known as the Fourier transform theory, if you're a physicist in the audience. So we have that. And I will also point out that if you add them up, it's equal distance between the crests. So it looks like there's just one color there, but there can't be. But that's the shortest pulse you can make for a given bandwidth. This is what us in the ultrafast business are always trying to do. All right, so now with all of those colors, we're going to put the pulse, short pulse, into an optical fiber. And an optical fiber is not like vacuum in that there's objects there, it's clear. And so that means that all of the levels, which I started the talk about how we're going to compare where the electron is, being held with a certain energy level, are up in the ultraviolet, and we're going through with maybe visible or infrared. So the question is, why did they travel different distances? It's because the photons want to talk to the atoms, but when it's a red photon, it goes, we got nothing in common. It runs through the glass. The green photon wonders a little bit. The blue is thinking they could be friends, but not really. So they talk for a while, but not really. And so this is why the red photons run through the glass, the green walks, and the blue crawls. And so after my 1.4 kilometers of fiber, I had a stretched pulse and a chirped pulse, right? And so it was about 300 picoseconds by then. All right, so once I had the stretched pulse, it was time to amplify it. And so the story I'm going to repeat because people told me they liked it on the bus. So this is just a dig at my friends in atomic and molecular physics, but I'm an optical physicist. And so only photons have personality on my talks, okay? So these are atoms. That's how you know. Now, in a laser amplifier, you have a bunch of atoms. And you have to excite the atoms. And so you use a different source. We used ultraviolet lamps around the rods. If you engineer it right, you will have at least about 95% of them up in an excited state. I don't quite know why the communications team thought they all had to be on the edge, but there would be at least 95% of them excited. Now, I told you the dye laser cannot be made energetic, and the glass laser can, but it has to be big. So why is that? The dye laser is like a sprinter, and the glass laser is like the marathoner. The dye laser wants to give up its energy right away. And so it would release photons maybe this way and cause emission all the way down. This would maybe let one go and cause amplification this way, and this one could let one go and amplify this way. So if you try to make it big, you end up with just a light bulb. But a glass laser says, I'm a marathoner. I can go a long, long time. I can wait. I can hold on to this energy for a long time and wait for a photon to come along. When that photon came along, you'll see it's the very same color as the excited atom. This means the photon energy matches the energy where the electron is sitting. But this time the electron is not down here trying to get up. That's absorption. The electron is in the top level. And another thing that Einstein taught us, it's amazing that he left some things for us to still do, because he did so much. But one of the many papers he wrote, 1916, was the theory for the laser. And so he's the one who showed us that if the electron's sitting in the excited state and you go in with a photon the very same color, it would be knocked down, and this is called stimulated emission. And the energy would go out of the atom and into the light beam, and the two photons would have to go exactly hand in hand. And so here it goes. Those two photons find two more atoms. They go hand in hand, and those four find four more. And so this is how all lasers starts. It starts with one noise photon going in the right direction, and after that, it's stimulated emission. But you can see that we've left most of the atoms in their excited state when we have these very few number of photons. And so we have to get out of this exponential growth region into the linear region, okay? And so we have to get up to what's known as a saturation energy flux. There is an energy per unit area that you need to get to. And I like to think of it as a snow plow going through the snow, but you can imagine whatever you want. I don't know if it snows here. So, so you need to have that energy or that number of photons per unit area. And so this is why if you want a lot of energy, it has to get very big, because we start with an oscillator with that one photon. So we use tightly curved mirrors and we go down to a tight little beam. And in that tight little beam, we get it up to 5 joules per square centimeter, but there's not many square centimeters. And then we go to an amplifier and we get the beam a little bigger, and then we get the beam a little bigger. And each time we start with that, you know, for glass, 5 joules per square centimeter. And this is why for a kilojoule, you had to get to a pretty big beam in order just to get that energy out, okay? So that's why big energy lasers are also big lasers and expensive lasers, so they shouldn't be damaged. Okay, finally, we have the compressor. Now, we've all seen light go through prisms or rainbows, and that means the different colors refract or bend different amounts. So we have something called gratings in our labs, and it just does it faster. So now you're going to watch, we had the red photons out ahead of the green photons, out ahead of the blue photons, and the red's going to bend more than the green, more than the blue. We're going to use 2 parallel ones, so they all come back off parallel. And when they do, it's a nice short pulse. And that's the whole thing. And so that's how we had a short pulse. My colleague, Steve Williamson, came in with his street camera one Thursday night, and we measured that it worked, and that we saw that we had compressed the pulse back to the pulse duration we were expecting, and we had all the energy. And so that was the whole experiment done. So once we had the laser, we were back to using it. Now, I told you I was going to do harmonic generation, but I never got to figure out how to make the medium. But also, and is this which Nobel laureate is speaking across the street? Who am I competing with? Anne Luthier, who's I know going to be at the conference tomorrow to tell us about her wonderful Nobel Prize winning work. She saw the 33rd harmonic before I even tried to see the 9th harmonic. So what was the point? She blew my PhD right out of the water. So I couldn't do it. There was no point to do it. So I was very lucky that Silong Chin came down from Laval, and he said, no, let's just do multiphoton ionization. So now, this is a different way to think about it instead of the basketball playing one. We're going to think about the electron. When I say there's levels, if you're going to ionize it, you have to give it enough energy to get out of this well it's sitting in so that it's free to leave the atom, okay? So this is, and if it was going to be this multiphoton idea that Maria Gopalmayer told us about, it was going to take 11 photons. I don't know if I actually have 11 there, but it's going to take about 11 photons to kick the electron out. It would go with the 11th power of the light we put on. It did not. So we hadn't seen this. We had now, the laser came along and brought us nonlinear optics. When CPA came along, we went past the nonlinear optical regime. We no longer had to think in this photon picture. It was back to being just a great, big, giant classical wave. And if you think about it that way, then you can think about it just tipping the well over, and the electron was free to leave. And so this is why I like to point out in this talk that you need both fundamental science to know what's going on, and then that brings us the new technology, and then the new technology keeps pushing the science. And so that's where we're at, and I'm getting near the end of my time, I'm sure. So I'm just going to show this plot of Gérard's. He's been showing it for many years. So the laser came along in 1960. It got us to quite a bit of intensity compared to the light bulb. These two things make the pulse shorter. Then we couldn't amplify. CPA came along in 1985. It did take 10 years. This is what we thought would be done with CPA when we created it, that the laser fusion labs would take their big lasers and use it. They were a little scared to use it until the technology got better so that we didn't damage their very expensive lasers. They also had to figure out, though, the last part, my gratings, was the problem. Okay, you could not put very much energy on those gratings. And so they spent some time figuring out how to make high damage gratings and large gratings. So we got there, but now when Gérard used to show this then, of course, he showed it more vertical and it was just a straight line, and we would be here now. We're not there now. So we are looking for people, very smart people, to come up with a new Nobel Prize winning idea to kick us on up. I've added these two dots to the graph since they both happened during COVID. The most powerful laser is in Europe at the Extreme Light Infrastructure. It's 10 petawatts, but they haven't got the most focused intensity. That record is being held by Korea at Corals. And they have a 4 petawatt laser now, and it's focused down to wavelength dimensions. And so we're at 10 to the 23 watts per square centimeter, just 6 orders of magnitude to go to get here. So we need a new idea. But anyway, if we get there, I'm just going to say, people ask, why do you want to get there? This would be what's known as the Schwinger limit. And up there, if you focused into vacuum, and vacuum you might think is nothing, but our high energy physics friends tell us it's not nothing. It's matter connected to antimatter. Our quantum friends call them vacuum fluctuations. Sort of all the same thing, I think. Anyway, depends on how you look at it. But if we could get to 10 to the 29 watts per square centimeter, we would have enough electric force to take the charged matter, the charged antimatter, and blow them apart. And we could just create matter out of nothing. So we're waiting for it. I hope to see it in my lifetime. I'm not working on it, but it'd be nice to see. Anyways, we're aiming for that, but I'm just going to finish my talk with how it gets used now. And the first use that came along was eye surgery. When LASIK was done, they used to reshape the outside of your cornea, but you would poke yourself in the eye. If you poke yourself in the eye, you know it hurts. That's because the nerve's on the outside of your cornea. So they now want to cut a flap, and then they still use an ultraviolet laser to reshape your cornea, but the cutting of the flap is done with my laser hammer. So I'm going to show it to you. It's only hard to watch at the very end, so you'll want to shut your eyes if you don't want to see the flap, but I have to show it to you. So you'll see that it's going to be, I think, a kilohertz laser. It takes 17 seconds. Remember, it's only where the light focuses down. So this, and it's clear, so it can go through the edge, inside, right at the focal spot. It will damage it, which is how you're cutting it. And you raster scan across, causing all those many, many, many damage points, and you've cut a flap. So this is the part that's hard to watch. I've learned to watch it, but it took a long time. A surgeon's going to come in here, and you have to be awake for this surgery. That's why I wear glasses. People say, why don't you do the laser surgery? Well, okay, because of this. Not the laser part. This part is gross. See, it is, isn't it? There you go. But it is a flap, and that's it. So that's what got me sitting beside the King of Sweden back in 2018. Thank you very much.
Wow, that was awesome. And it wasn't exactly the same at all as the first version, which is why we have to listen to things more than once
Yes.
to understand them. Thank you so much. Now what we're going to do is we're going to ask you to take a seat over there in this beautiful white chair.
Let me just take this
And
down so
our
everyone sees.
colleagues are going to come and move the pedestal away
Okay.
and make sure we don't break this beautiful computer. Great. And then I think I shouldn't move it just in case. Is this your personal
Yeah,
computer?
yeah.
Okay, so you definitely want to keep that
Yes.
safe.
Mhm.
Maybe you want to put it on that. Okay, there. Mic that's going to work. Thank you to, is it working? No, not yet. Thank you to all the staff that are helping to make this possible. And also, if you can let me know just now if we get questions from the online group. We've got about half an hour. I know people are very, very tired. Some people have been at conference from beginning of, 7:30 today. And some of you have been having full academic days, so I'm feeling very tired. But this is a chance for us to dig in and ask questions that probably will. I know, she challenged me yesterday and we could fail. I could fail spectacularly. She said to me, she was very, very polite. So she didn't quite say it the way I'm saying it. Is it working now?
Yes, it is.
Okay. Very politely, not the way I'm saying it now, Donna said something like this. Gosh, I've been interviewed a lot of times. Well, I have found online 72 interviews. And I have found biographies in 25 major English language newspapers. So that's excluding the corpus of interviews done in French, in Spanish, in Arabic, in Mandarin, and in other languages such as Hungarian and Russian. So I'm pretty sure that Donna is somewhat jaded about typical questions. So I'm really going to try and take her in some slightly different directions. Please let me know if this mic is turning off. Felt like it was turning off. Is it still working? Okay, great. So I've spent a lot of time reading some fantastic articles about you by some of the top science journalists in the world. And it's a tall order. One of those outstanding interviewers is sitting in the room. And I'm so happy to acknowledge her because in English, she has the same name as me. Hello, Catherine. Do you want to give everyone a wave? I think one of the best articles that I've read was actually derived out of an interview that you did with Donna some years ago as part of the fantastic journal that you helped to bring into being. And its English language version, I think, would be tremendous if people wanted to come and talk to you a little bit about it just now. And you managed to winkle out of Donna some really interesting insights that probably come from the fact that you're an English major before you're a scientist. Anyway, that's just my personal view. So as we've all heard, Donna, the breakthrough paved the way for the LASIK surgery, for the smartphones that we're all carrying around today. And we'd still be living, as you said, in a nanosecond world rather than exploring the physics of the femtosecond dynamics that happen millions of times faster. So what I wanted to ask, as a person that has had an impact with your colleagues, who you generously always acknowledge, in fields from chemistry to atmospheric science, non-linear quantum electrodynamics to laser-driven manufacturing, where do you think the next leap forward is coming in these borderland science around your space at the moment? I've never found anybody actually ask you that directly.
I have my own mic.
Oh, great.
I also have too many mics. Mine's loud. I almost don't need a mic. Okay, which of the most exciting in all of the fields? That's a tough one. Yeah, because my usual answer is I'm still waiting for laser acceleration to really work. I'm not saying it doesn't work. If you're working laser acceleration, of course it works. But it is funny some of the times, because I'm work on science policy a lot now, and I think we in physics have to accept that public policy people understand health as being something to fund more than something else. And so I've noticed that my colleagues who know how to get their physics into medicine, you know, have more money. And so I think that would be good. And so we're trying to compete with that and trying to get the laser accelerators to the point that they could beat at least the hospital accelerators, right? Now, Gérard wants to beat CERN. I'd like to see that too. That would be fun. But that's going to take, that's a bigger challenge. I think that we are on the cusp of beating medical accelerator or hospital accelerators. So that would be a good combination of medicine and lasers, yeah.
Ask that question. And I hope that you're all thinking of a question to ask Donna, because we're going to make sure there's a chance for that. All right, fantastic. So my second question starts like this. On October the 3rd this year, Nature published a very interesting article that I know everyone's been reading. It's called How to Win a Nobel Prize by Kerry Smith and Chris Ryan. And they crunched the data on 346 prizes since the beginning of the 20th century, and there's 646 winners. And out of this, they come up with many intriguing findings. And this one really struck me. John W. Strite, who won the Nobel Physics Prize in 1904 for his work on the property of gases, has 228 academic descendants with Nobels. His students, their students, and so on. You can do the maths. That incredible lineage is drawn back to one person, sometimes with gaps between them, but a steady beat through the entire 20th and early 21st century. It's extraordinary. They're not all Nobel laureates in physics, but they're in allied disciplines. In other words, they're not in peace and literature, and they're none in biology that come from his lineage. Just think about that. 228 Nobels from one Nobel Prize winner. And you can work on that lineage. I'm a historian. It's very easy to see biographically and through people's publications, their laboratories, their ideas. Right. So where do you trace your lineage from? And Donna, where do you think your descendants will fan out to over the next 100 years?
Most of my students go into industry because there's more money there. And I can't find a postdoc because they're all going out to industry. Because I'm doing fiber lasers now.
Postdoc here in the room right now, yes.
If you're interested in working in short pulse lasers, talk to me. So that's where my lineage is going. And where is my lineage? Of course, I actually, you know, my PhD supervisor is the one I won it with. So he right away already had one person right there. Yeah, I don't know that I've worked under other Nobel laureates though. I'm trying to think of who I've worked under. Paul Corkum didn't get it last year, so I was his postdoc. Yeah, I don't know who my lineage is, and yeah, I don't know how many of them. Maybe you can still go to industry and win. So they did this year. So
we're going to be watching that space. I won't be alive anymore, but there'll be somebody in this room who writes a paper in Nature in 30 or 40 years' time, and that will answer that question, which will be very exciting. Coming at you from a slightly different space, you've described yourself and been described by others as a laser jock. And a quote that's attributed to you goes like this: as an experimentalist, you need to understand the physics, but you also need to be able to actually make something work. And the lasers were very finicky in those days. So, having read a little bit about your childhood and your parents and some of the things you did before the age of university entrance, here's a question for you. What made you so good with your hands?
Well, my favorite toy was Lego. I did like building Lego. And so this is still, if you look at any laser that I've ever played with, pretty much, it's Lego size. I actually, as of my undergrad, I did have to do something that required me attaching a piece of silver wire to this little semiconductor thing I'd built. And my hands shook under the microscope so much I couldn't do it. And the technician I was working with thought, what is wrong with you? Everybody can do this. And so he thought the solution would be to he look into the one eyeball and I look into the other. And I thought, this is not going to work. Now my hands are really doing this. And so he said, you're no good at this. And so then I went, okay, I'm no good for small little things. And then when I worked with Paul Corkum, his laser, he gave me the choice of either using his dye laser. So I did finally get to use a dye laser, or I could have worked on his CO2 laser. And I saw the crane in the one room. And I said, what's that crane for? He goes, that's how to lift the lid off the CO2 laser. I went, okay, you have that one. I'll take your dye laser one. And that's how I decide. So I just play with Lego size lasers, and I'm very good at it.
I'm sure that a cartoonist in the room could depict this. And I'm thinking that maybe your son, who's studying to be a stand-up comedian, could help us understand how to portray that. And that also makes me very excited to think how maybe one day there'll be a Nobel Prize in humor, one of the most difficult areas of human imagination to achieve. And it would be wonderful one day to have your son on the podium with you to actually draw out the tragic comedy that's also involved in this complex and very long journey to become a scientist.
Well, can I tell you about my son, the comedian, saying this? When he was in high school, he said, Mom, you're not funny. And I said, well, sometimes when I give talks, people say I'm funny. Mom, you're not funny. You can think you are, but you're not. So then he came to Sweden with us and he listened to my Nobel lecture. And then he said, Mom, I still don't think you're funny, but I can see why your colleagues think you're funny.
Well, that kind of could be an insult to other physicists. I'm not sure. That's like a teenager.
Yes.
Insult mom and then insult everyone.
Yeah, no, he was an adult.
Fantastic. Okay, I look forward to meeting him one day. So this is perhaps in a way a bit more of a typical question, but I think I've got a twist on it. When you were enrolled as an undergraduate at McMaster University in Hamilton, Ontario, Canada, we learned that you were torn between electrical engineering, where there were lots of jobs and still are, and physics, which perhaps unusually you said was obviously more fun. Luckily, your university, which was not common in Canada or in the rest of the world, allowed you to do an integrated program. You didn't have to choose. You could do this hybrid. And better yet, as you've yourself explained, electro-optics and so on were part of it. And so you graduated with a Bachelor of Engineering, with engineering physics as a major. So thinking about that, if you were designing a university program right now and you had all the resources you needed in the world, what do you think is vital in your field and related fields to really grab young people's passions and to move them towards excellence in these areas? What kind of a program would you design?
That's a tough one because I want people to be careful. Lasers were, to me, were just a cool thing in the 1970s because you didn't see them, right? And that's why I thought this would be so cool to go to a program where 1/4 of the engineering physics program was lasers and electro-optics. So I was out recently out west in Canada, and people asked me a question about, what I would recommend to students. And I said, you can't just go with the biggest bandwagon. You can't just go along with what everybody else is doing. You have to figure out what you really find fun to do, because to do really well, you have to work very hard, and you're going to work much harder if you really love doing it. And I got an email from a former undergrad who was in the audience, but did not come down and talk to me. It was so surprising. But anyway, because there was a crowd around me, so he didn't. But he said, I really appreciated that answer because, I just thought it had to be quantum. And nothing against quantum. He went into the quantum field because everybody 20 years ago was going into the quantum field. And he really felt like he didn't really love it. And he's no longer in the quantum field. I hope he is still using his PhD, but in a data management way. But, you know, I think that is true, is that it's hard to say you could make a program that's really going to appeal to a lot of people. I think what we have to make sure we always do at universities is make sure that we have many types of programs, because we all think and act and feel differently. And so what we have to always have is this wide plethora, if not all at one university, certainly, you know, countrywide and what have you, you have to be able to offer all these things. And they have to still be single disciplinary to multidisciplinary to transdisciplinary, because different people want to do different things. And we don't know where the next big idea is coming from, right? And so we have to make sure there's room for everybody to work on everything.
I hope South African decision makers are listening to you, because we have a lot of programs that are very siloed and where there's huge penalty for young people to move sideways and around corners. And that probably is a great disinhibition compared to some of the universities in the North and the continent, say in Ghana, and certainly some in Europe, North America, and other continents. So thank you for that. So in South Africa, sociologists and historians and theorists of gender and psychologists have described a phenomenon that is often, in a kind of shorthand way, described as a patchwork quilt of inherited systems of patriarchy. So multiple cultures with people from all different parts of the world, including indigenous societies, with only one exception, the Lobedu people of the realm of the Rain Queen, imagine the world through the lenses of a naturalized, male-ordered society. And when these came together, they overlapped and reinforced each other. Now, in your own context, you've described the story of women's disappearance from academic faculty positions after graduation as being part of what you called, in my mind, very memorably in a number of interviews, a two-body problem. I'm just going to quote you briefly so the audience can come with me if they haven't read the same interviews I have. Men outnumber women so heavily in physics that straight women who want to marry have a much wider choice amongst their colleagues than straight men do. If they marry a fellow physicist, however, it becomes almost impossible for the couple to find long-term university jobs at the same time due to the relative scarcity of academic roles. And almost always, a wife's career is subordinated to her husband's, which is another reason for the smaller number of women who ultimately remain in science. In some ways, in the journey of your life, the roles were reversed, because Douglas Dykar, who you married and who got his doctorate in electrical engineering from Rochester, and you have 2 children together, he ended up going into industry and took up other roles, and you stayed in academia. But given this journey that you've taken, the observations that you've made over your lifetime, have you come up with a way of addressing this particular challenge in science education, given that it's unlikely in your lifetime you'll be able to solve the question of gender inequality and the rearing of children and the making of homes?
Well, I mean, I think the bigger problem in science is the fact that there's just very few science jobs. So this is why it's really tougher then to get, it's kind of like the nonlinear problem. You get the 2 photons or the 2 bodies into a small spot at the same time, and it gets to be tougher. And so just to straighten out a little bit, I didn't stay in academia. In a way, I got back into it, although I was in Princeton. Doug was at Bell Labs, and I followed him. And I took a job as a technician at Princeton. So I actually stepped off the academic trail. So again, for young women, a lot of people who say, oh, you have to be so careful when you have your babies. No, you do not. Just do it whenever you feel like it. But I got back into academia. And so then Doug followed me and took an industry job. Now he keeps saying when it's his turn again. But we moved close to my family, so I don't know, it's hard.
He still has a chance, and he's holding your laptop.
I know.
So, I
have a very supportive spouse. I do.
Thank you for that. Okay, so I found it, of course, extremely exciting, and I jumped up and down when I read you talking about the 2-body problem, because as all young people in this room know, and probably most people that are my age too, the 3-body problem, the 2008 novel by the great Chinese science fiction author Xu Liu, the first part of which was serialized and then only turned into a put-together novel a bit later, portraying a fictional past, present, and future where the Earth encounters an alien civilization from nearby star systems and sun-like orbits, and is, for me, as a non-quantum physicist and non-physicist, one of the most exciting, complicated, challenging books I've ever read about quantum physics and quantum mechanics. And as many of you know, the English translation was published in about 2014, and also by a person with the surname Liu, which in South Africa means lion, very exciting, and which won the Hugo Award for the best science fiction novel, recently been turned into an English pay-for-view television series after the Chinese one launched a few years ago, I think in 2015. I got to thinking, what books have electrified you in your life? What books do you return to? What books do you remember? Are you a reader of books?
Probably not. So I mean, that's a long way to go. There would definitely not be science fiction. I hate science fiction. I walk out of movies when the science seems so stupid. So I don't like science fiction. I will have to say a few of them. Okay, one, I mean, the only book I've read a billion times was my dad had to read Molly Whoopie to me as a kid, to the point where he just almost brought tears to his eyes thinking, not one more time. And because that was about a younger daughter who had to use her spunk and intelligence to save the two older sisters. Yes, I thought my daughter would love it, but then when I read it all those many years later, and I'd forgotten why I loved it so much. She only had an older brother. She didn't appreciate it at all. Anyway, that's why I read that book over and over and over again. The older sisters were beautiful, but it was the spunky, intelligent one that saved the day. The other one that I read a lot over the years probably is more, well, Lord of the Rings. That's not really science fiction, is it? I love Lord of the Rings. I've read that many times. I don't know why. And, but I also read Pride and Prejudice quite often. I think that's a real feminist novel. And I'm not a feminist, but I think that's a great novel.
Thank you so much. Okay, so in the course of your PhD research, it's clear from all the interviews you've given, and people can read them online, that ideas moved backward and forward between you and your advisor, your supervisor, and there were sparks in either direction, and there were provocations, and there were dead ends. What is the key to scientific excellence? Is it money? Is it recognition? Is it time? Is it support? Because when you've been asked who's inspired your work, and tonight you gave her immense credit as well, you said that you drew on research by Maria Goeppert-Mayer and Marie Curie. You pointed out in several interviews that she didn't have a paid job for at least some time, I think maybe even for 2 decades, but I've only looked at her Wikipedia page. I haven't been able to find a book about her yet. So even though she was doing incredible
OPN
work.
wrote a great article back 10, 15, 20. So OPN wrote a great article about Maria Goeppert-Mayer.
Okay, I'll have to look that up. Thank you. But it does seem to me that for over a decade, she didn't have a paid science job. Mm-hmm. And you point out, I mean, I'm not going to repeat what you said this evening because it was so beautifully expressed and so clear, that some of the profound insights she had were not visible, partly because of the lack of the invention of some of the laser tools, but there could have been other reasons too, if you were less generous, that people didn't pay attention to it for that long. So, okay, she didn't win the Nobel Prize for it, but it actually did change what could be done. So you've said, you know, how can you go for more than 20 years, not to not get a Nobel Prize, but not even to be recognized as a scientist, and yet to persist? So clearly some people persist without encouragement, without money, without resources, without recognition. It's not ideal, is it? What do you think is the key to excellence and persistence then?
Well, for her, luckily, she was a theorist, so at least she didn't need experimental money. And her husband made enough money for them to live on, so I don't think she needed.
There's the key.
She didn't need to make money. But I mean, there's a lot of interesting stories about Maria Goeppert-Mayer, because when we were at Argonne National Lab, there was still a scientist there who had worked with her all those years ago. And so for some reason, and I don't even know why, he went and looked up the performance review of her during the year when she did her Nobel Prize winning work, not the year she won, because she was already in San Diego by the time she won. And she got an average rating. The only thing she scored high in was works well with others. That's because the women do that. Otherwise, on her productivity that year, she got average. And so there was, you know, so I do want to keep saying that things I think are getting better all the time. I think when I talk about it, that's the point, is that, so in one of the jobs, so her husband, I guess, was a very good chemist. She was obviously the better physicist, but let's leave that aside. He would get these good jobs at these good places. And the one before Argonne was the first place. University of Chicago and Argonne was the first one to pay her. She would get to be a scientist. She could get jobs as a secretary. And then she would do half-time secretary, and then they allowed her to stay in the office so she could work on her theoretical ideas within a physics building or something, but she only got paid to be a secretary. So times are really changing. I don't know, I have two thoughts about the recognition thing, because for each of us that gets this huge, humongous recognition, other people do not. And so this is my thing against recognition. You know, it would be better if none of us needed it or wanted it. And so it's the double-edged sword, I think, the recognition part. Pay obviously is nice, so let's not have that. And again, I think some areas of science require more money than other areas of science. And so I really hope that governments see that and appreciate that and fund accordingly and fund well and see. And so I talk a lot about public policy and science. Places like Korea, where they spend 5% of the GDP on science and research, and they spend it wisely. They don't just spend it, right? It's not just throwing money, right? I mean, because probably other people can turn to ones that spend a lot of money and it hasn't worked. But they spent it in a way that really made sure academics, industry, and government all work jointly together so that they all jointly benefit. And so you watch Korea, that at the end of their war, just in the 50s, so it's just 70 years ago, their gross national income was just $67 a year. I mean, that's how incredible it is. And they've pretty much caught up with the top, you know, they're now a top 20 country, and their, you know, per capita would be up in there. And so they've gone from a very poor country to being a wealthy country using science and doing it well. And most countries should look at that as an example, and there's a few others in the world that have done it so well, and think, okay, now they also work too hard in Korea, but so they have to come a little ways back. But other than that, you shouldn't have that kind of pressure on you. I just think it's incredible that if you do it right and do it well, if governments could understand what a scientific boon that is. Because I'll tell you the other example. I first went to Korea in 2011, and then I went to Russia, and they get a fast train, which bugs me because Canada, for some reason, can't have a fast train, but all right. We're told it's too large a country with not enough people, whatever. But I'm on this fast train, and I see 3 billboards in a row: LG, Samsung, and Hyundai. And I just thought, oh my goodness, I've never been anywhere to see 3 Canadian billboards for these big companies. And I thought, how did Korea do this? So that's when I started thinking about Korea. How did Korea come along so fast? And it's because they really figured out how to do science and research well.
Thank you for sharing that with us. Yeah, that's coming to the end of my questions. So I'm going to look out into the audience for at least 4 or 5. One of the things that intrigues me is last year at a university in Johannesburg, we held a big, in a sense, retrospective for the life and times of a South African Nobel laureate who won his prize not that different time to you, called Sidney Brenner. And he was nominated in a number of different fields, but in the end won for biology, a very famous geneticist, but also a medical doctor who also worked in computational science and AI and across many fields. But he said in his autobiography that he regarded his greatest achievement as being noticed by the Emir of Singapore and being invited to Singapore in the 1960s to help develop the National University, where he helped to create a curriculum that he kept trying to get Wits University and other universities in South Africa to think of, and was continuously spurned. And yet there was this forward-thinking view. And
look how well Singapore is doing there.
Yeah,
they should go back and think about it again. I know.
That's why I'm thinking of it. So I think you can tell all of you that Donna spends a huge amount of her time on different kinds of committees and bodies talking about policy and about young people and about funding, and gives a huge chunk of her time to committee work and other such things, stretching right back as far as I can see to the late sort of 2009 up to 2013 period when you were already taking up leadership positions, which I think is also relatively unusual for a person who ends up winning the Nobel Prize. But another person, if any of you are interested in looking up his life and times, is a boykie born in Germiston, whose name was Sidney Brenner, who went to university when he was 14 and taught himself English. So thank you so much. Those are my questions. And now I'm looking out to see, I hope at least some of them were new. And there's a gentleman over there with his hand up. We've got this fantastic staff here who are running around with the mic. Maybe we'll take 4 or 5 or 3 if they're very long. Please try and keep them fairly short so we can get in a few. Over to you. And would you be so kind as to introduce yourself? That would be lovely.
My name is Joseph Indeke. I'm a theoretical physicist. My question is the following. In your lecture, you have emphasized the importance of intensity, of wavelengths, and duration of the pulses. Can you comment on the possible importance or actual importance of the polarization of the light, the spin of the photons, in your discoveries and or in the applications that you mentioned at the end of your talk?
Okay. Thank you. Yes.
Store that up.
Well, he really wants, I mentioned many of the optical properties, but not polarization. And one of the other many talks I give is how to use light to measure things for the environment. And this is one of the things that, we said, why would you use light? Well, light can do so many things. It can change its direction. It can change its wavelength. It can change its polarization. And each thing tells you something different. And so the change of polarization is important. We used it to switch the light in and out of our amplifier, right? And so we needed to be able to rotate the polarization. And that was the first problem that I came across when I was trying to do this work, is that we were the first people trying to put a large bandwidth into an amplifier. So we used a standard amplifier way of, amplifying a YAG in a glass. And we ended up getting ripples in our spectrum. And we realized it was an etalon from the wave plate we were using to change the polarization. And so we had to take that element out of our laser and figure out what to do without it. And so we did have to think about polarization, because that is a standard way to switch things in and out. So that's the way I would have used it, more than all the other things that are now, the beautiful angular momentum and all these other polarization states to study for that. But it is one of the big things we play with in light, it's true.
Thank you.
Is anyone else?
Oh, for those of you not in optics, just so you see, when we say there's an electric field, linear polarization points up, points down, points up, points down, but it could also go around in a circle, and that circular polarization and everywhere in between we can get.
You got a lot of people nodding. So there's a question over there. The mic can go there.
Located to the mic.
And please feel free to ask questions. There's no stupid questions in this room.
Only stupid answers. Off we go.
Thanks. Please introduce yourself as well.
Good evening. My name is Hartman van Staden. I'm currently an engineering student here at the university. I noticed in your lecture, you specifically showed the transmitted light, I guess is the more, or one of the correct terms to use. You showed the emitted light's person as upside down. Was that an artistic choice, or is there something specifically meant by that?
Oh, okay. So when we usually show our graphs, a photon going up is being absorbed and a photon coming down is being emitted. That's just the way we do it, because we think of the light going up into another energy state and being lost. And so I guess that it's, if the atom gives up its energy and lets go its photon, it is the atom that's gone down, not the photon, but I guess, I don't know. We always show it as photon, or arrows going up and arrows going down or coming out.
Thank you.
I had not thought about it being confusing in my, because I went to a lot of trouble to make that one come down.
There you are, man with a cap, almost in the middle. Person carrying the mic around is getting her steps in for the day here. Please introduce yourself.
Hello, my name's Ben. I'm studying electrical engineering here. I'd like to ask you a non-science or engineering question. To work on something your entire life like you've done with dedication and to achieve at the highest levels like you have takes an enormous amount of grit and perseverance. And I was wondering if you have a life philosophy that's guided you towards that goal.
Yes, and you know, a lot of people point out that it was my very first paper that won the Nobel Prize. So it has been downhill since then. But I was in when it was published, right? I was in my 5th year of my PhD. That's how many failures I had had, okay? And I started working on it in my 4th year of my PhD. So I'd had a whole lot of failures. And I've had a whole lot of failures since. And so when I'm ready to kick my laser, and I am ready to do that a lot, I know not to. And then I go for a walk and I just think about it. I love to walk. Gérard loves to swim. He tells me he gets his ideas swimming, but I like to go for a walk and then, I don't know, just let my mind go. And so I calm down. But I am a very happy person, just, you know, and so I only stay down for short amounts of time and then I get myself back up. But I'm just a natural. But I will also tell you for my PhD, I had decided in elementary school that I would get a PhD because I heard it was the ultimate in education and I knew I belonged in school. And so I knew I really, really, really wanted this PhD. So that also kept me going. And when I thought, oh my gosh, I'm never going to get this, knowing that I really wanted it, I think kept me going.
Thank you very much.
Thanks for that lovely question. And I remember in one of the interviews, there was a description of your dad and the role that he also played, as well as your mom in encouraging you. And apparently at one point he said, hey, why don't you try out for the astronaut program when Canada, you know, was getting astronauts going and you were very good at maths and STEM subjects. And you had already decided, no ways, you're going to do this PhD. That was much more important than being an astronaut.
But also I get my claustrophobia and my fear of heights from him. So I don't know, he wouldn't have done it either. So I don't know why he thought I would do something so scary. No, obviously not.
Yeah, we have a question in the front and I'm just looking to see if there's 1 or 2 more hands bubbling under because we're going to start up. There's a person there. Fantastic. We've got 2 eager
right
people.
here.
So person with the white shirt in the front, then the gentleman with the dark shirt sitting about 8 rows back.
Hi.
Please introduce yourself at the beginning.
Hi, I'm Michael. I'm a student here studying physics. This question has 2 parts. You spoke a little bit earlier about recognition. Is there any part of you which kind of regrets winning a Nobel? And then do you ever get frustrated at how overlooked the rest of your work is?
And because we're running out of time, we're going to ask if that person, can you pass the mic back? Oh, you've already got one. Fantastic. Okay, we'll go straight into the second question. You can do like a double whammy answer. And please introduce yourself.
Okay, hello, my name is Angel. I'm an Ecuadorian physics student. And my question is about professional success. I would like to know, what does it mean for you? What's your perception of professional success?
Oh, as long as I'm happy, I'm successful. So I'm not somebody who's really trying to save the world. I'm not somebody who's trying to get the most citations. I'm not trying, I just like playing in my lab. And as long as I'm happy, if I can keep my students somewhat happy, I'm happy, we're all happy. That's all that matters. Now, your question was about, do I want to give back I have thought about giving, could I give back my Nobel? Sometimes I find the pressure too much, right? And I get asked a lot about the imposter syndrome. And I said, and I've heard other Nobel laureates say this too, it's like having the imposter syndrome on steroids, because people think you're so smart because you won a Nobel Prize and you're no smarter than you were the day before you won and nobody thought you were smart, right? And so that's a lot to wear. But then on the other hand, without it. I have met Brian May of Queen. I have met the Pope. I have, met my prime minister. I mean, I get these incredible opportunities simply because somebody somewhere decided to give me the big award. And so, obviously I won't give it back because I like the big moments, but there are times when I find it frustrating.
And plus, you probably wouldn't have come, or maybe wouldn't have come to the most beautiful country in the world, right? The one that you're sitting in right now. Everyone, can you join me in thanking each other and Donna for a really fabulous discussion? Okay. Oh, thank you for being so generous. We also want to just say one last time before you get up and go, thanks to Prof. Sibo Moyo, who couldn't be here, and Jackie Dutoy, a professor also associated with the program, who's been unbelievably supportive. The whole FPP team. If there are people here from UJ, from the next cohort, we see you, we support you. We're on your team. To ASAF for their support and funding, to Himmler for being here this evening, to the ICO 26 conference attendees who are still going back to more exciting papers the next couple of days, to NITHIX, if that's how you pronounce it, the National Institute for Theoretical and Computational Science, to Professor Francesca Petroccioni, who's giving his inaugural tomorrow, for all of his support, to Yasira Ismail, to all of our colleagues, to all the people who did the tech, to the photograph, cameraman, to all of the wonderful people who've helped with the mics, and most of all to you. And we have a small gift from this province for you. And these are these beautiful proteas that grow wild on the mountains around here. And although you probably think you won't be able to take this back to Canada, I don't know what the rules are, but they can actually last dry for weeks and weeks. So I'm not sure, but maybe you can try and get them in. And even if not, you can still enjoy them the next few days. Yes. And this is a beautiful gift on behalf of Stellenbosch University that I'm giving you. Everybody, one last time.
Thank you very much. Thank you very much.